Okay, so what have you learned during the last lecture? Nothing, just messy things. So we defined at the end of the journey, through viscoelastic circuits, that we can define an SLS, standard linear solid. It's a model. Playing with the model parameters, we can try to tune a system that is reacting in one fashion on short time scales, on a different fashion on long time scales. Okay? Applied to the Earth, we can use that concept, trying to model the response of the system on short time scales, the wave passage time scales. And we understood that if we measure the Q of the Earth as an integral value for normal frequencies, let's say up to 1 Hertz, Q is pretty much constant. It's a band. It's about 100. Could be largely variable in materials, but as an integral measure, it's about 100. And so we have to superpose different SLS, trying to reflect possible microscopic mechanisms that are physically responsible of an elasticity. And so we created an absorption band with a constant Q. The final consequence was that to be causal, we need time dispersion in the definition of P and S velocities. It's an intrinsic dispersion compared to the waveguide dispersion that we studied for surface waves. The end of the story that to treat an elasticity, we have to make K complex, if you want velocity complex, elastic moduli complex, and this means anelastic moduli, viscoelastic moduli complex. So that we can understand how part of the energy during the wave passage mechanism is lost in friction, in something that is not regular inside the Earth. And the clear manifestation of this effect here is that if you give a look to some wave recordings, given a source that now we understand how, we pretty much understand the kinematics of a source, it's radiating with rise time, with rupture time, blah, blah, blah. Okay, but during propagation, some effects could be evident in some regions with different Qs. And this is one effect. Same source, pretty much the same distances, but recorded in different parts of US, for example. And you see that this signal here has a totally different frequency content. High frequencies have been absorbed. Why? Well, if you think in terms of intuitive physics, high frequency wave system is sampling more a material than a long period one. Sampling more cycles, and every cycle you're going to lose part of the energy. So if you think about when we make, I cannot use the blackboard because it's not recorded, but if you think about making the K complex, the imaginary part that is e to minus kx in some way, in K there is omega. So larger is omega, stronger will be the attenuation effect. And that's a clear manifestation. Okay, now, from now on, we will try to apply these concepts and other concepts that we have studied during this course, like for example, source effects, propagation effects, and just a brief snapshot about what we can call site effects, how the seismic signal collected at a site can be used for seismic hazard. So from now on, that's why the conclusion of this lecture here was about something a little bit different, that is a bridge between a picture that we have seen when we defined Richter's magnitude. Richter found that plotting amplitudes versus distance, there was a trend. And with logarithms, then the trend was becoming stable. Okay, so this is pretty much the same vision of a summary of a wave field through what? Well, the maximum. That's why peak is here, and peak will be a keyword for today. What does it mean? Okay, for example, you take the signals here and you take the largest. Pay attention. We can use different domains: displacement, velocity, acceleration. You do know that going from displacement to acceleration, you're pumping up frequencies there that can be removed from the signal during propagation. And you can call PGD, peak ground displacement, PGV, PGA. And PGA is what is mostly used and abused as an indicator of seismic hazard. Now, that's a plot of peak acceleration given a source with distance. Now we know that going on with distance, on average, we have a decay, geometrical spreading, and an elasticity. So that's why what were called attenuation laws, actually attenuation relationships, there is no law. Attenuation stands here because, on average, amplitude is decreasing. Please do remember that source effects can change this regular pattern here, directivity. So if you stand in front of a rupture, stay in the back, the same source is felt differently. Radiation pattern, it's something that is 3D, the 4 laws, you do remember. So distance is not the only factor that is changing amplitude. But on average, we are waiting for a decay. Okay, in this plot here, you see some curves, and the most important difference is between magnitude 7 and 6. Okay, it could be Richter's, it could be MW, so moment magnitude. Let's say that we define an energy released at the source, and of course, energy is going to be revealed in amplitudes, because energy is proportional, kinetic and potential, and part of it is removed, but with the square of the amplitude. Okay, given the same energy, for example, if you take these two curves here, magnitude 7, you see how different they appear. So there is a generally different trend there. Why? Because Eastern US, on average, has a larger Q. So seismic propagation is more efficient there than in the Western US, where we imagine a very highly seismic zone, but with many fractures that are defects when you propagate. So part of the energy is lost there with a rate that is higher than compared with Eastern US. And you see that in terms of peak amplitude, for Western US, having a magnitude 6 and the magnitude 7, for example, in California, are giving pretty much the same value. And we have one order of magnitude larger there. And we know that magnitude is a logarithmic expression of energy. So if you give a look to this curve here, from let's say 20 or 30 kilometers on, a magnitude 6 is causing the same effect than a magnitude 7 in California. Now, what about hazard? Well, looking at this picture here, one could say, well, Eastern US is more hazardous than California, because you need less energy to cause the same effect. Now, what about hazard? This is what we are going to think about in this lecture. And this is a picture that is a little bit outdated, but not that much. And it is a summary of what we have done until now, because you have a geographical area, let's say two events, and in principle, with all the uncertainties, they have the same magnitude, 7.3. So the same energy is released there, the same antenna is there. The antenna is different, actually, a lot different. There are a lot of differences for orientation, for self-faulting, This can be called an intraplate event. This, of course, is on the San Andreas system. So strike slip, here it is a mess. Look at the date. Now we know that the Lander's earthquake is during heavily instrumental seismology. While the New Madrid earthquake, actually it seems that there were at least two, or a sequence, we don't know, is definitely in a historical area. So here we have a lot of uncertainties. And this is the realm of intensity. So those maps here can be drawn just thinking about intensities. No seismograms there, no seismometers. Lander's is a heavily instrumented earthquake. But with all the uncertainties, we see that the pattern of what we can call isoseisms is totally different. This one is much broader. So the signal emitted by the radio there can reach much far distances than this one. Now, based upon this picture, can we say that New Madrid zone is more hazardous than California? You could say, no, come on, California is much more active. But one can say, yes, but if one event is occurring there, well, a mess will happen there. So we have to find a sort of a compromise between different effects here. What can we do is try to estimate ground motion at a site, and then to decide what to do. That's the topic of seismic hazard. So until now we have learned during wave physics seismic wave propagation. During this course we have learned, I hope, some basics of source effects, seismic radiation. Then we added some concepts about elasticity. And now we have to use all these tools trying to define what is hazard. And that's the topic. Now, how to start? Well, let me tell you that it's not easy. That's a human picture. What can we do is try to start with some definitions. There are many definitions, and I put here on these slides just 3. One is a little bit outdated, but it is maybe the first one. It's coming from a beautiful textbook that is about earthquake hazard, made by Leo Reiter a long time ago. But it was the first textbook in which there was a clear distinction between hazard and risk. And hazard, you will see a slide in just a few minutes, but is trying to divide the concept of risk from hazard. They are not synonyms, definitely. Hazard is something that is nature decided. We cannot modify it, we can assess it on strict terms. If you, of course, add here the adjective seismic, it's related to earthquakes. Some primary effects of earthquakes, like faulting, but not many cities are built on faults. Well, some of them. But we know how the wave field can reach a site, also when it is far. And today you will see also an extreme case related to site effects. However, we should try to define the effect of an earthquake at a site, at a city, so a urban scale, at a region, at a nation, because the end of the story is a national hazard map. Okay, there are some primary effects, like ground shaking. There could be some secondary effects, like landslide triggered by an earthquake. I cannot cover the topic, but you can imagine that there are some phenomena that are triggered by earthquakes. Now that's hazard, and hazard can be defined in a region given the sources that could affect that region. Now, if that region is a desert, you could say that the hazard is high there, but maybe there is no risk. Because what can be called exposure is zero there. Or vice versa. you can imagine that the same earthquake, let's say magnitude 6, that in Italy could cause a lot of damage, as you have heard in some recent news maybe. If you take the same earthquake and you put it in Japan, style of faulting is totally different there. Subduction, here it's compression, extension. Here it is a mess, but on average, the style of faulting and seismic activity is very different from the Alpine Apennine region to the Japanese trench. But let's imagine to take the same event there and we put it in Japan with the same conditions. Vulnerability is totally different. And exposure is totally different. The same to US. There are no middle-aged towns there. So vulnerability is totally different. Now, when you convolve hazard with vulnerability and exposure, then you get risk. Okay, that's the main definition. And of course, you can try to act on vulnerability and exposure. So you can try to reduce risk, better assessing hazard, and try to reduce vulnerability. That's the main message for today. So in this case here, that's the definition that you can find on this. Usually seismic risk is assessed or decided or computed on a probabilistic level. So trying to take into account what is the probability or the percentage of money that we can lose if some events are happening. Of course, you can take the adjective seismic, you can replace it with, and this is what we're going to do in the last lecture, put in tsunami, that is another phenomenon that usually with the largest manifestation is excited by earthquakes. Or you can put there landslide, you can put there, I don't know, avalanche, you can put there whatever natural hazard. For today, seismic, and it's enough. And you do understand that when you couple the concept of hazard, that as etymology is coming from French, lazare, that is coming from Arabic, and the roots of the term hazard are in rolling dices, okay? Let me tell you that in Italian it's totally different. It's called pericolosità. It's related to danger in some way. And danger is something that is coming from nature, usually. So please remember the distinction between hazard and risk. Other two definitions here, and you do understand here, this is by John Anderson, that is a sort of a guru of hazard assessment. Okay, on the first part, you see again, that's the physical phenomenon that we should try to understand and to assess. And you see that there is the verb may. Okay, it may, depends on then on the anthropic tissue that is there, how far it is, how vulnerable it is, and so on. But here, it's the computation of a probability of a consequence and its economic cost. A third one that I like a little bit, because here again, it's the physical effect, may produce, and here, probability of a consequence, like structural damage. And you do understand that when you speak about risk, now you have to imagine an interface between the seismological, the scientific community, and, of course, the engineering community. Then there are other interfaces, maybe with social and political, but those are non-linear, we're not to touch them. So these are the basic definitions. And if you want to take it simple, you can imagine a sort of a product. It's better to describe it in terms of a convolution, because vulnerability, that is an engineering issue, exposure is an economic issue, usually described by a matrix, for example, like fragility curves or something like that. Maybe you're going to talk about this with Stefano Parolai in this course, I'm not sure about that. But for today, we will focus on this, on the hazard. And please do remember that according to strict definition, it's nature decided, okay? We can try to assess. While on the other side, the vulnerability case is man decided. we can try to design or to restore existing buildings or design new buildings, trying to get lower vulnerability levels. Okay, and usually the probabilistic risk computation is given a set of events, their probabilities, and their cost. Is this on your slides? Okay, good to know. It should be there. Now, before going to the core of today's lecture, let me show to you the first maps. Now we are going to hazard. For some slides we are going to hazard. And that's it. Well, you can call this the oldest seismic hazard map. It has been made by a Scottish scientist that was one of the first seismologists, Robert Mollett. We're at definitely pre-instrumental era here. So the only way to assess hazard at that time was to go around, walk, and look at the effects. So it's like intensity-based map. And Mollett was traveling through Italy, and there was the Naples earthquake at that time, so you see it here. It's very dark, the color here. Then he was visiting Spain, so he was remembering about the Lisbon earthquake here. Some events in the Middle East. Then he was traveling also here in South Africa. That's why you see a dark color there. But of course, no instruments, no networks, just, how to say, human history there. And personal trips to some places. But that's the oldest one. It's nice. What's next? Well, this can be called the first technical one. And if you see the, okay, it's, at the time it was Soviet Union, and you see it has been delivered by Moscow Institute of Physics of the Earth, and that's still there. 1937, and you do understand that now some instruments were there. If you remember the brief lecture about seismometry, Galitzin instrument was there. So the first recordings. Why I like this map? Well, it's not very quantitative, as you can see, but it's an attempt to put dark areas with danger and lighter areas with less danger. But of course, this is limited about the knowledge, the geographical knowledge. In some way, here it is also coupled with the density of population, because risk at the end of the story is coupled with population. While hazard in principle can be studied without taking care about the distribution of people or exposure. Of course it is, but okay. And this is one of the first maps incorporated into a building code. Doesn't mean it's a sort of a holy book. It's not that holy for engineers to say, okay, if you want to build something, could be a bridge, could be a dam, could be an hospital, could be a school. Now you do understand that the relevance of the building is increasing the risk, apart of the hazard. So building code should take care about this. In Italy we have now the NTC 2018. We have a sort of a Eurocode now. Many countries have codes, their own codes. And the code is a tool based on hazard and risk assessment to provide something practical to engineers. So that's the first one, to be incorporated into a building code. And now we are going to the basics. This is really the slide to be saved for today as things to remember. And it's a sort of an historical trip about the hazard assessment techniques, traditional ones. Let's say that this vision was definitely valid until 2000. Nowadays we're trying to overcome this stuff here. Now these two terms here, two letters, P and D, stand there because on one side you have probabilistic hazard assessment, and on the right side you have deterministic hazard assessment. And now we will try to understand the differences between them. Let me tell you that after a seminal paper by Cornell, 1968, he's an engineer, he was an engineer, I think he passed away quite recently. But he published a paper about probabilistic seismic hazard assessment. He's an engineer, he was an engineer, so he wanted something to be computable. And to say, okay, what is the probability of something? That was his answer, his approach, and it's in its basics incorporated here. And you have to know that around the 70s in the US there was a strong debate about which route to follow. Please do remember that now NPP, nuclear power plants, had been disseminated through the world on both sides. And NPP are definitely relevant. So the topic was tough. What should we do? You do understand that an MPP is not an ordinary building. So at the beginning, they decided to incorporate the deterministic. Now we will try to understand what it is. While in the years after the 90s, definitely probabilistic was winning the competition of this dualism. Let me tell you before going to give a look to these two plots, that actually there is no dualism, if you want. They can be done together. Now, I promise not to touch the blackboard, but I need. Well, maybe we can. It's just a matter of recording. Now, let's try to follow these two apparently different routes. And they are different. Definitely they are different. Now, let's imagine to have a site. Here and here. We have a site. So someone is coming to you, maybe the mayor of a city is coming to you and asking, okay, please, that's the municipality of a city, or here there is a bridge, we are going to build an hospital, can you assess the hazard? Now the first thing that you have to do, and in my opinion, it's the most difficult step, is to identify the sources. So faults. So, okay, that's the site. Let's take all the faults that could possibly affect the site. Now, the most intuitive approach is to put there the nearest ones. But you think about now and you say, but there could be a larger one, magnitude, more distant, that maybe can cause stronger effects than a nearer one, but smaller. You have to compensate this. So maybe you have to try to take into consideration all of them. How far we should go? That's a good question. Let's say 100 kilometers. We will see later, but that's not easy. The most important, the hardest difficulty here is to identify all of them, because most of the faults are hidden. We're not in California where strike-slip faults are evident on the ground. Maybe we have subduction zones, Japan, Chile. Maybe we have blind faults, Alps and Apennines are full of them. So you do understand that it's not easy to identify them. That's why the study of catalogs, past intensities, is very important. And of course, catalogs that should be as complete as possible, but it's not easy in some regions of the world. I'm sorry to say that, but maybe the Italian catalog is the most complete of the world, due to all civilizations with written culture there. Greece, China. But for example, a country so complex like India, for example, is not easy to have a complete catalog. Many regions, many different civilizations, many different cultural traditions. So part of that information is lost. Okay, so catalogs. And then the next step is to ask to the geological community, geodynamics. Please remember that we have, let's say, 2,000 years window. But what if seismic cycling in slow regions? Maybe it's going to take 10,000 years. So we have just a tiny window on a landscape that could be much broader than what we see. Please do remember that instrumental seismology is, let's say, 100 years. So it's nothing. Okay, so the first step is to identify sources. Easy to say, not easy to do. Okay. Then we have a set of sources, but we can characterize them with magnitude, how strong is that radio, and distance of the receiver to the radio. Okay, MR. Yes, the Richters. MR. Good. Now we have a difference. And that's one side, important side, why probability is different than deterministic. And I think something should appear here. Now, on one side, probability is saying, okay, we have different magnitudes, but usually larger magnitudes are occurring less often than smaller ones. Now you do remember GR law, Gutenberg Richter. They performed it at a global scale with all the events that they had at that time. So here you have a magnitude and you have a lowering of the number of earthquakes with that magnitude occurring in that time span. Here on this side, the determinist is saying, no. Our target is to take into consideration the worst. So we don't care how much often they occur, let's take the worst. So immediately you have a dual way. But this, in principle, is more conservative. Let's take the worst. If we prepare a defense for the worst, then we are fine with the other ones. While here, you're trying to weight the occurrence of large ones, saying, okay, but they don't occur so much often. So it's a difference. And you have to think that at the end of the story, hazard assessment plus risk assessment is also a matter of money. Sad to say, but so if someone is reducing a little bit the hazard, not the hazard, the risk, maybe we can save some money. Okay, let's get out from those considerations. But let me tell you that this apparently is more conservative, but there is a dark side. It's not easy to say which one is the worst. Actually, no earthquake is the worst one. It depends on the building. And maybe you realize this immediately, thinking that different buildings are sensitive to different frequencies. That's why there is no a single worst bad one earthquake in a region. Okay, but let's say that now we have decided, okay, you have the worst, you have the bad one. So you have the magnitude and the distance. Here you have many earthquakes with many magnitudes and distances, but some of them are occurring more often than others. Third step. This should appear later. Third step. Well, actually, this is a common traditional step. Now, given the magnitude and the distance, how can we assess the ground motion? Okay, the engineers are saying to us, look, we don't care, this is the traditional message of the 70s, we don't care too much about your ground motion with source and blah, blah, blah. Please, give us the PGA, big ground acceleration. Well, if you think about it, if you have an acceleration, the maximum, you multiply it by the mass of the building, you have the maximum external force. And you can do what is called some rough dynamic analysis. Okay? You are done. F is equal to MA, Newton. So we don't care too much about all your seismological stuff. Please give us PGA. That's why traditionally there were at that time called attenuation laws or relationships. Nowadays they are called GMPE, ground motion prediction equations. But the idea what is, okay, let's make a plot of something, traditionally it was PGA, versus distance for different magnitudes. It's Richter. So that we can go to a distance of our site. In our case, for deterministic, just one. We take the curve of that magnitude, we go here, and we take a value. And for deterministic, the game is over. But wait a second, because you see here there are many dots. You should say, of course. The same magnitude at that distance can be very different around the world. I can have a strike slip earthquake or a deep slip, different depths, different focal mechanisms, different radiation patterns, different side effects. You have scattered there. It's nature. So, attached to this value here, usually there is a log normal distribution with a scatter. But the end of the story here is, okay, we have bad PGA for that earthquake, the bad one, with that magnitude, with that distance, plus minus something. End of the story. On this side here, that is the probabilistic stuff, we have something different, sorry. Okay. We have to take care about all the magnitudes that could affect the site. And now we have different curves, different magnitudes, and different distances. Okay? So maybe use the blackboard. That's beside, that's one source, that's another one. Let's imagine this is larger, this is smaller. So we have M1 with R1, M2 with R2, and M2 is larger. Okay. So there, we are going on two different parts, different magnitudes, larger distance, this is smaller but maybe shorter distance. Now we have two measures. Okay, the probabilistic is taking into consideration all of them, weighting them for their occurrence, GR law. So in some way, this is weighted less than this one, because in one time span, it's less probable that it is occurring. You compute this sum, and the end of a probabilistic hazard assessment is called an hazard curve that is giving here a given probability of exceedance of some parameter, usually PGA, and here you have a probability, a value. It's tricky. It's tricky. And that's why, since it is the most common practice nowadays, what we will do now is a sort of exercise in doing this. Well, the right side is pretty much obvious. Okay, we select the worst, will be the largest magnitude. Okay, if you have a larger one very near, game over. That's been bad. For Kobe, for example, 1995, the fault was from magnitude 7 point something beyond the city. Game over. But in many cases, we have different M's, different distances, so it's not easy to decide which one is the bad, which one is the worst. But let's imagine that we do that, game over. We come out with a number. Here we can come out with what is called an hazard curve. And we have to take decisions. We have to take decisions here because here, traditionally, you have an annual probability of exceedance. How long should be our time span? Traditionally, it's 50 years. There is no nature in 50. It's just a reference, human scale. Someone is saying that that was the time for which an agency in US was responsible for a nuclear power plant. That's why 50 is important. But there is nothing there. Okay, 50 years, and then you take 10% in that probability. It's a decision. Why then? Okay. So he's saying because the wife of Cornell in 1968 was a statistician working for epidemics. And so she was very acquainted in statistical analysis. And in that field, 10% was, in a totally different field, was the proper value. But traditionally, it's 10% in 50 years. And that's why a map, is made. Traditionally, now we're doing something different, is like that. Now, this is the first. It's a little bit outdated nowadays. It's made around 2000. But it's the first global seismic hazard map. G-shape. Now you see red, white, and green. So you do understand what are, at the first glance, the hazardous places. Well, in some part we know subduction zones, compressional zones, that are very complicated. You see, also Italy is quite red here. Now, how to read this map? What is written here? Okay. That map is produced using one hazard parameter that is very specific. It's peak ground acceleration, PGA. Here it is written in meters per second square. Usually we use G. But, okay, 10 meters, roughly said, per second square is 1 G. With a 10 probability of exceedance in 50 years. 475 return period. Immediately you should say, oh, there is an earthquake that is occurring every 475 years. That's the first impression that you, when you read this. 10% in 50 years, and that's the probability. That's the value. For example, if you stay here, you have a 4.5 meter per second square, so let's say 0.5 G, that has a 10 probability percent of B overcome in 50 years. I don't know you, but every time that I read this, I get crazy. I cannot understand it. But it's a value, it's an indicator. Okay, now let's try to understand how this is made. With a simple example that has been done by Ned Field, but he's a very good seismologist, and nowadays he's working for, I think he's still working for SCEC, South California Earthquake Center. He was one of the most active seismology in producing hazard maps for US, and he produced a beautiful 3 pages paper that you have, no, this one, I was interested in about anomalous dispersion this morning. It's this. You have it on your website, on your portal. Okay, keywords, probabilistic seismic hazard assessment. The acronym is PSG. A primer. And the first part, now we are going to do it. So your homework is to read it carefully. I will ask you this at the exam. Probably not, but probably. So you have a 10% of probability of being asked this in, let's say, 20 days. Okay, now the first picture is beautiful. And that's the new concept that I want to provide you. Now you should say, come on, except the building, that is the first part, we know all the other part. Because we attended wave physics. That's a pendulum. I'm very happy to use my lab. Now, what is that? Oh, it's this. We studied during the wave physics. We studied in theoretical seismology when we were dealing with seismometers. I'm the ground shaking, and this is trying to stand, okay? And the difference between this and the ground is giving us the ground motion. Today, this is different. This is a building. Well, not in this way, it's not easy, but it's a building. It's a skyscraper, it's 20 stories building, it's an ordinary building, okay? Different lengths, different periods of this simple harmonic oscillator are mimicking, I think it's in English, different buildings. So we create a simplified version of the building in what is called a SDOF, single degree of freedom system. Yes, the one that we studied. And that's the first step. And the second step is to remember that every SDOF in nature has some damping. Engineers traditionally use 5% of damping. Please ask me, 5% of what? Most of the engineers do not remember what is 5%. It's 5% of the critical damping. Yes, the critical damping that we defined during the wave physics course. Do you remember? Yes. When we compared omega 0 and gamma, there was critical damping. Okay. A building on average, because you can imagine that masonry building, reinforced concrete building, they have different dampings, but on average it's 5% of that. So it's relatively weak damping. 5% of the critical. It's not overcritical, it's not strong, it's weak, 5%. Good. Now we have a building. And if you want, you can imagine to have a table here with many buildings, skyscrapers, and you can imagine, okay? Well, actually, that's the vibration of a bar. It's not a pendulum. It's less linear. Okay, smaller, I cannot do the ordinary buildings, okay? Imagine to have a set, long period, short period, okay? Now we take this table with all these beautiful buildings and we shake it. We can. That's the earthquake, that's the seismic input. All of them will oscillate differently. According to the frequency content of what? Of the acceleration, not the PGA, the acceleration in time domain. Why acceleration? Because we have a single degree of freedom with forcing, and forcing has to be acceleration. So let's imagine that we have acceleration shaking the table. All of them will oscillate differently. Remember resonance. The frequency content of the input will decide which one will oscillate stronger with larger amplitudes. For each of them, we take the maximum amplitude. We plot that with the period of that building, and we create what is called response spectra. That's why this picture here can be explained by this one. I had prepared two different versions. Now, that's our table with the different buildings, okay? To all of them, we provide the same input, the same forcing. It's the current motion acceleration, okay? They shake. They have a time history of shaking. For all of them, we take the maximum. You see they are different, longer periods, shorter periods. Now we take the maximum and we plot it versus period. That is what is called response spectra. Please do remember one thing. The most used response spectra are acceleration response spectra. What does it mean? That here we are considering the acceleration of the buildings, okay? And we take the maximum, we measure, and we plot it. We can do the same with velocity of oscillation and displacement of oscillation. Those are called spectral acceleration, velocity, spectral velocity, spectral displacement. By spectral, the engineers mean this. It's not Fourier spectrum. There is a relationship, but it's not a Fourier spectrum. So now we made a further step. Seismology, if you want, is this, is acceleration, understanding acceleration, but not the PGA, the time history. Provide to a simplified version of buildings and study here period and assay. That's called spectral acceleration. That is nowadays the most used seismic hazard parameter. Why it's much more important than PGA? Because now the engineers can study, can model the buildings, identify the most important periods, go here and to look for the maximum acceleration at that period. And so they have now not PGA, but they have spectral acceleration with the period label. Now, can you tell me if we can read PGA here? Let me tell you that the answer is yes. Because, okay, skyscraper, less stories, less, no, let's imagine that this is vanishing here. This DOF, single degree of freedom oscillator, going from 10 seconds, 9 seconds, 8 seconds, 0 seconds, that's PGA, because there is no more building. So when you read the maximum of this here, when there is no building, that's PGA, of course. Okay? So you take this, shorter. The end of the story is simply acceleration of a graph. That's why the most important hazard quantity nowadays is called SAE. And it is measured in acceleration, because now it is an acceleration. So it can be measured in G, most used by engineers, meters per second square, centimeters per second square, and so on. For one event, it's something like that. Here you read T in seconds. It's not the time of the accelerogram. No, it's the period of the buildings. And when it is 0, here you can read PGA. Just there. Because a SDOF with 0 period is no SDOF. That's the acceleration of the ground. Okay? So that's why here I was proposing to you the two sides sharing the same concepts here. Seismology, forcing a set of SDOF with different periods, shorter and shorter. Here you have 0 if you want. And what you can do is to plot the maximum here. This curve will be the response spectra in acceleration. If you do the same in displacement, sorry, I found just this one, and I don't like it because now here it is 2%, usually it's used 5%. It's in inches, sorry, okay? But that's the concept. You can do the same and plot here the maximum displacement. That is called spectral displacement. So one message to take home is that hazard, it's not easy to be expressed. You can take a number, you can take a curve, we will see now how. But the most important quantity that is used today is not PGA, but it is SA at different periods. PGA can be read here. Okay? What's next? Let's go with Ned here. And let's try to give a look to his, what is this? To his example. Now, please do remember your homework for Friday is to read this. If you don't trust me, it's 3 or 4 pages. Oh, wow, it's longer. But the most important ones are just 3. For example, let's give a look to this. Now, what do we have here? Well, we have a set of sources, as we have seen, with different magnitude, with different position, okay, respect to the site, and different rate. That's the Gutenberg Richter in some way. That's our set of sources. What can we do next? You will read later, and that's your homework. Let me tell you, your homework can take 5 minutes. can take also 2 hours, but it should take just 5 minutes because I will ask you one thing to be computed. Now let's go here. Ground motion model, attenuation relationship. Nowadays they are called GMP. That's one appearance. If you remember, that's the third block in both deterministic and probabilistic. That's a more modern appearance, magnitude, distance, usually it's logarithmic. The message to take home here is that you have a scatter of points, those that can be experimental points, okay? You do understand that different zones of the world will contribute to this. That's why usually they are regionalized. But different sources with the same magnitude can contribute to that. Different radiation pattern. So there is a scatter here. What you can take is to take the average and to assume that the distribution here traditionally is PGA, but you can use also SA at given periods, is log normal. What does it mean? If you take the logarithm of this, you see that's the logarithm, the distribution around the average is normal of a logarithm. That's why it's called log normal. So what does it mean? That if your site is at 40 kilometers, for a magnitude 7.5, you can go here and you read an average value and a distribution. So you can take 1 sigma, 2 sigma, 3 sigma. 3 sigma will let you to go infinite. But that's a problem. So that's nowadays called GMPA. Nowadays, it's not only in PGA, but it's also in SA at different periods. Okay? Okay, what's next? That's the tricky part. Now, what to do? Well, now we have a magnitude, we have a distance, we have a value of PGA, and now we can ask, what is the probability that that value is overcount? Well, if you assume that it is log normal, we know how to compute these integrals here. Because it's normal, it's Gaussian. I think you attended some physics course, experimental field, did it 30 years ago. You have the tables with this function. Nowadays you have computers. So what is the probability that? Okay, you take numbers. What you can do is to compute for that event with a given distance, with a given magnitude, that value, that is the logarithm of PGA, is larger than a value. Okay? You can do that. Because you know that you have a distribution. Okay, when you compute those integrals, you can come out with this. It's a probability that a value is larger than a reference value, given the earthquake at that distance. Okay? It's log normal, so you can compute this. So, the ground motion parameter, traditionally logarithm of PGA, but nowadays also logarithm of SA at 2 seconds, for example, has this distribution that is larger than. Okay, it's a curve. It's probabilistic. That's the first factor that will enter into the probabilistic computation. Now, what's next? Now, the probabilistic flow, now we were in the third block in the writer scheme. Let's go back and remember the different magnitudes at different rates. GR law. So any event whose giving a probability larger than a value of a PGA is weighted for its rate, annual rate. Okay? Now, for all the events, it's probabilistic. It's not deterministic that was taken that bad. All of them. Now you compute this sum. You sum all of them. You do understand that some component points here that will be have a larger probability. Now they are weighted less because the magnitude is larger, so in some time that will occur less frequently. And you can compute this sum here. Now what is entering here? The log normal distribution that is providing this, and Gutenberg-Richter that is providing this. It's okay? Now the tricky part. And in my opinion, it's really tricky. Okay, now let's assume that the distribution of earthquakes is Poissonian. What does it mean? Well, we can use a distribution of probability. Please do remember that Poissonian distribution is referring to independent events. But we do know that earthquakes are somewhat related in clusters. But okay, let's assume we do understand that if we release some stress drop in some place, then maybe in the next 10 years, probability is changing. Well, that's not Poissonian. Poissonian means, okay, it occurred today, it can occur also tomorrow, and vice versa. Okay, now that's the key point. The probability of exceed that ground motion in a given period t, capital T. Now your homework will be to go back to that t. Okay, what is this probability? Well, the probability of overcoming this in a period t is 1, to be sure, minus the probability that those events will never occur. That's why Poissonian is useful. It's this. Okay. The output is called hazard curve. Still, we have to make the last two steps. So what we have done until now is the following. We have decided the sources. We assume distances and magnitudes, and we have went there. We have gone here, okay? For each event, we have a value, we have a distribution, log normal, and we can compute the probability of overcoming each value in that distribution. Each event then has an annual rate, R of n, coming from this. Now we weight all these events by this, and we consider the probability of overcoming a general value of ground motion given all the events. So what we have to do is to sum all of them, and 1 minus the probability that none of them will occur. Please do remember that we've used many assumptions here. Log normal, GR, Poissonian distribution. Then we can compute an hazard curve. Okay. Now, what Medfield is showing in this paper here is a practical example with a very simple case. A site that is affected by two events, just to show how these things are working. And they are very specific, typical for US, but okay. We have a magnitude 6 occurring every 22 years. You do understand that we don't know this, but okay. 7.8 occurring every 300 years. Strike slip, 10 kilometers, so the same distance. Okay? Now, can we make an hazard curve for this case? Okay, let's try. What you have to do is to take those two magnitudes, go up, look at the distributions, and compute what is called R1 and R2. What is R1, R2? This. So you go to the logarithm of PGA, you compute this curve for both. You multiply then by the Rn. Remember that 1 over 300 is different than 1 over 22. You take these two factors and you sum them. Okay, there you go. So you see, this one, for example, R1, is getting larger values here. Okay. For smaller values of PGA. Well, that's intuitive. Since that earthquake, maybe it's occurring more often. With a typical value that is this one, this will be the typical value that will occur. This is the rate of exceedance per year, because R of n is the rate of exceedance of value of events per year. So we have in that place, let's say, a 0. How much is that? That's 10%, okay? Okay, because it's 10 to minus 1. So we have until here a 0.1 G of being overcome, 10% probability of being overcome in 1 year. Well, it's quite large, but the value is quite low. The other curve is giving lower probabilities because now it's 1 over 300, but of course here it's giving larger values. It's a magnitude 7.3. Now, since we are taking care of all of them, we have to sum, and that's the hazard curve. Now, how to read that? Can you give this to I don't know, headmaster of a city? He or she is going to look at this and ask it, so what? So, should I wait for 2G? Well, maybe yes. It's probable. I mean, it can happen. But if you read here, is saying that in 1 year you have pretty much 10,000 times the probability, 1 over 10,000 that is occurring. One is thinking and saying, okay, it will never happen, right? So low the probability. Okay, goodbye. On the other side here, you could say, okay, but look, here you have a 10% of probability to occur in 1 year. Oh, 10% is okay. But what is the value? Is 0.03 G. So let's design for 0.03 G. You know that's tricky. So you can design for more frequent events, for lower values, or very rare events, but larger values. Now, which road to follow? The one, usually, that is saving more money. Now, the last step is the following. Since this curve here is not easy to be interpreted by an engineer, the engineer is saying, okay, let's consider a time span. Let's take 50 years. Now, with 50, here, somewhere, the rate of exceedance has to be multiplied by 50. Okay? Step number 1. So, you're interested, since you are planning, maybe you have to get a license for a nuclear power plant for 50 years. Okay, let's give a look to 50 years. It's a decision. It's not related to seismic cycle. You take this curve here and you multiply by 50. Okay. Now, and here you have the total probability. Now let's take a threshold. Of what? Well, of the probability of being overcome in both 50. Pay attention. There is a typo here. These two arrows are referring as have to be reversed. But let's give a look to this. Now, we have a 50 years time span. Now we can decide, okay, let's take the 10% in 50 years. It's a decision. You go here, you go to this curve, you got this number here. Okay, it's 0.6 G. Okay, that value has the probability of 10% to be overcome in 50 years. You're done. You put the number on the map. Well, you have to know that in the last 10 years, especially in the US, they realized that the values with that indication were too low with respect to what was happening. But if you think about it, okay, that has the 10% of probability of being overcome. It can be overcome. So you do understand that following this approach, you have a map that is an indication that is always valid. It's simply telling that it has the 10% of probability of not being being overcome. Okay? So maybe what is occurring is that 10%. You do understand how tricky this thing here. And that's why in recent years, the hazard maps in US have 2%. Now 2% is this one. You go here. Now you have 1G. Ah. So it's much larger than the other one. So I hope now you do understand what is the game, but it's not a game, but that was leading to this definition here. It's the PGA with 10% of probability of being exceeded in 50 years. Now, let's try to decompose all this messy part here. Actually, the rough decision here, in my opinion, is to decide between a percentage pair. 10% was considered to be acceptable. Nowadays, we are going, in Italy, for normal buildings, we have 10%. But then, for other buildings, relevant buildings, you have to try to play with other parameters, but actually is reducing T. It is the same. But I don't want to enter into these details here. By the way, that decision will cause a number there. But until this, if you divide by 50, because 50 is another decision, maybe the best map to be used is this. This is what is called hazard curve. And now you do understand that it is this one. It's a parameter, usually PGA, but nowadays is SA at a given period, with the probability of being exceeded in 1 year. Now, what is your workshop, your homework? You have to demonstrate, it is going to take 1 minute, well, to read this again with these numbers, re-understand it, and you have to tell me why, okay, this curve is made summing terms like these ones, where the log normal distribution is entering and the rate is entering. You have one event, you have two events, you have 1,000 events, you have to sum them. That sum will contribute to the final hazard curve. Then, as a last step, usually, you decide some years, 50, and you multiply that by 50, and you take a percentage. Now you have to tell me why 10% in 50 years is equivalent to, say, 475 years of return period. That is exactly what is written here. You see? Everything is based on Poisson distribution. That's the hint. With this hint, you should make it in 1 minute. The second, that is going to take, if you solve the first, it will take 1 second, is to tell me what if you take 2%? Because this is what is used in US, for example. Now, first homework. Tell me why this is following this. Oh, no, the question mark is not here. Second homework. Which number should I put here? And third, that is a philosophical one, is to tell me the return period of what? It's written there, return period. So my question to you, I'm very unpolite, is return period of what? That's the third homework. I'm going to take 10 seconds.
I don't get it. What the return?
Oh, that's my question to you. Look, here it is written, 475 years return period. What is a return period? It's something that is occurring every 475 years, right?
That's a little quick.
I'm asking to you, what is occurring every 475 years? It's a simple question.
An earthquake with certain
Wrong.
G
An earthquake? No. So, you see, now you're waiting that every 475 years, an earthquake is occurring. No, 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 no. That's the trick of probability. So let me solve to you the last. If you give a look to the net field, and if you do the first two homomorphs, please do remember this. It's a sum. It's your homework. Please take your time and answer. You can do that in 5 minutes. Okay? Now, let's conclude this lecture with some slides here that want to be, I will be very fast now. They want to be some hints, and I'm using something that we have already seen. Please do remember that beyond this standard definition of seismic hazard, we know many other things that cannot be squeezed in a Poissonian, Rn, and so on, especially in the GMP. Please do remember that we have source effects. What does it mean? That the acceleration time history can contain many tricky things. And displacement time history can contain many tricky things, like, for example, this. And you're going to study that with Alessandra for a different reason, but please do remember that we have static displacement there. Engineers had begun to be interested to that. Do you remember the Sir George Stokes that was solving the Green's function in the near field? Okay, they call it fling. If you have 1 meter of tilt and you have some buildings there, maybe it's important. We studied that. Near field. Then we studied also directivity. And this is the Landers 1992 as seen by two receivers, so the same source, pretty much the same distance. You do understand it's the same. MR is the same, but due to directivity, the signal is totally different. One is shorter and larger, the other one is longer and smaller. What about PGA? They are totally different. And the input is totally different. Okay? So source effects can be very important there. And what is more important, and you're going to develop this also with Stefano Parolai, are site effects. Now, that's the most extreme event, maybe, that we can imagine. It's tragic, but it's beautiful. Sometimes it's called the Mexico City earthquake of 1985, September 19. Well, it was not Mexico City. The damage was at Mexico City, but the earthquake was 400 kilometers far. So you see the distance here. Okay? Now that's the earthquake in a subduction zone in the Pacific and Central America there. Magnitude was about 8, and distance was about 400 kilometers. Now, wait a second. 400 kilometers? Where should we go? 400 kilometers are out of scale. Should be nothing at 400 kilometers. Am I right? 400 kilometers is like from here to, not to Rome, but to Florence. Okay, tragic but beautiful. Give a look to the time series. Okay, this one is your good old friend. It's this one. Acceleration in the near field, or near source. It's very rich of high frequencies, right? Radiation is there. Now you know the source spectrum. Large magnitude, just a few stronger in long periods, but high frequencies is there. Look, it's beautiful. Acceleration, velocity, displacement. Okay? It's that one. But, okay, sorry for that. Okay, now it's getting smaller. Yep. After 300 kilometers, the wave train has been relaxed. Some long periods are still there, an elasticity. Okay? When it was arriving, UNAM is the University of Mexico. It is a sort of a city inside a huge city. Quite relaxed, but a little bit larger. Now let's give a look to this. What was happening there? Side effects, resonance. The answer is resonance. So after more than 300 kilometers, the wave train was arriving in Mexico City, DF, Distrito Federal, and so it was with the maximum peak was about 1-2 seconds. 1 second is, okay, it's a long period. It's not the acceleration that usually is important, okay? And this is what has been recorded in Mexico City. In 400 kilometers, now, this is a beautiful picture in my opinion. This is for one event, that's response spectra. Now you do understand what is this. That's the period of the harmonic oscillators, forced by an acceleration. And you see that those between 1 and 3 seconds, long periods, as a rule of thumb, every 10 floors, there is 1 second. So here we are with buildings of 20, 30 floors. Okay, large ones. Resonance. And what was occurring there is that the local sedimentary basin, that was quite thick there, was taking these 1, 2, 3 seconds and exciting them. So it's like resonance when I'm making this pendulum to oscillate near its resonance. So out of phase. No differential motion, but if I force it at its period, wow, that's a resonance, we know. Okay, resonance was occurring between 2 and 3 seconds due to side effects. All the buildings whose resonant periods were there were feeling a strong excitation and they collapsed. This is why more than 10,000 people, maybe 20,000, people died there for an earthquake at 400 kilometers. It was crazy. That's why, please do remember that in your beautiful attenuation relationships, or GMPE, sometimes we have bumps due to side effects. That's why side effects are in the codes nowadays. And why in Mexico City? Because Mexico City is the new 2.0 version of Tenochtitlan. But at that time, Tenochtitlan was built just there, with the Aztecs. And it was surrounded by a beautiful and huge lake. And they used this to defend their city. Actually, the Spanish conquistadores took more than 10 years to conquer that city. And after their conquer, you see these were the bridges that were defending the city. They, and in the last 400 years, humans tried to fill that lake, creating a paleo lake lacustrine sediments, thickness there that could be also 200 meters. And so you see that's nowadays, and that's Mexico City nowadays, 200 meters of sediments, low velocity sediments. And that was the reason for amplification, local amplification. And if you give a look, this is the map of a city. Here you see tiny, but very strong here, with amplification related to amplification of sedimentary basins. So please do remember that in seismic hazard you have to take care about also some other natural effects like source effects and site effects. If you want to squeeze all, okay, and this is what happened in Mexico City, that many tall buildings with relatively good design collapsed because they were not designed to sustain such a large acceleration at those periods. Because after 400 kilometers, okay, you're waiting for pretty much nothing. Mexico is quite a large active zone, but we were taking care about acceleration coming maybe from magnitude 6 nearby. And this means accelerations at shorter periods, but they can sustain, but not at their periods. Okay, so that's a resonance. That's why please take care about what I was calling here site response estimation. It has been coded nowadays in the codes. We are going to speak about this, I'm pretty much sure, with Stefan. Okay? When this course is going to start? Is the course going to start?
Yes, on 18, if I remember.
Of February?
Yes.
Okay, good. He's going to speak about this. So please do remember local amplification. And one way trying to decide the importance of site effects is trying to map the subsurface topography and soil characterization. You have to know that the largest used and abused parameter is what is called the S30. You are going to use it. Stefan, let me tell you in just 1 minute what is that. Let's imagine to have a sedimentary basin with some, oh well, I have a picture later, I think. Wait, okay, something like that. Now, there are two important effects for site response estimation. Well, the first one is simple, is amplification due to low velocity. Do you remember the model that we use for lava waves? Low velocity layer over hull space? Do you remember the model that we considered for lava waves? Wave physics? It was a low velocity layer with a hull space. And we studied waveguides. This was beta 1 and this was beta 2. Okay? At that time we were thinking about crust and mantle. Now we think about low velocity layer, maybe the layer in Mexico City, 0.2 kilometers per second, layer sediments, over something that is rock. This is called bedrock. Let's say 1.8, 1.2 kilometers per second. So this is very low compared to this. What's going to happen here? Trapping. 1D trapping can be explained by a very simple formula that is telling to you that the resonance frequency of this system here are beta 1 over 4 times h, and this is h. Now if you use log wave equation, you can get the same. This is the fundamental, and these are the other ones. 1, 3, 5 odd numbers. You should know why. But I'm sure that you don't remember, because this is a free surface. And this is pretty much a rigid surface. So it's like a column with a closed end and an open end. Or a string with, okay, first, second. If you remember, there was a 4 there. Okay. So when you stay with 1D effects, what is important is the thickness and the value of the velocity. That is what is called 1D effects. And these are what usually they are coded for side effects. Now what is VS30? Well, you do understand that local amplification will be decided by the strongest impedance contrast. You do remember what is seismic impedance? It was the multiplication between density and velocity. So here, where is it? Here, you have a strong impedance contrast. Now, you don't know how much is important, but definitely this is the thickness that is important. Well, nowadays, also if we are trying to overcome this limitation, the value of the velocity that you use for site effect estimation is a sort of a weighted velocity in the first 30 meters. Now you should say, why 30 meters? Because 30 meters is the depth that can be reached on average in 1 day of drilling. So if you don't want to make it 2 days drilling, 30 is what you get. And that's expensive. So now you compute an average, a sort of an average with thicknesses of this velocity until 30, and you use that. Now you do understand that in Mexico City this is nothing if you have 200 meters. Okay? But usually it's used as VS30. The second important thing, please do remember that if the world is not 1D, but it has irregularities here, you can imagine that the wave field there is going to focus and defocus, like in this example here. And you can see that you don't have a simple 1D effect here, but if you give a look to these two signals taken 600 meters, it's nothing. Apart, they are totally different. So side effects in 2D or 3D world can contain much more information, can be much more variable, because you do understand that inside the basing, you're creating what they are called basing edge waves, that are additional to your wave reflection and refraction, that physics, okay? And complex subsurface focusing. That's why I'm taking this statement here that was used by Ned Field in another beautiful paper. Please do remember that simple laws can be very useful, like this one, but in some cases they are not telling the whole truth, of course. And please do remember that when you have this case here, and if you imagine different sources with their antennas, the focusing can be very variable. So what is highlighted for one source, for one radio, maybe it's not the same for another radio, because they are coming from different directions with different directivity. So it's a mess. That's why usually there is an intrinsic variability. But we should try to code that. So we've seen today the standard approaches to seismic hazard, probabilistic. You understand how tricky it is, and you're going to play with that. Deterministic is saying, okay, we don't care. Let's take the worst. Now, using this picture, you do understand that decide what is the worst is not easy. Because no one at the time would have been choosing an earthquake at 400 kilometers. That was the worst, but for buildings between 20 and 30 stories. For an ordinary building, that's not the worst. So also the deterministic has intrinsic limitations, because there is not a single worst case earthquake. There could be many according to the different buildings that you have there, for a dam, for a bridge. So in some way, the new hazard assessment is a combination of these two cases, considering many scenarios. That's why I prefer to call it multi-scenario. Maybe using some modeling, especially to study before the earthquakes occur, if you have some data about the site that you want to consider. And maybe if you want, you can add then the GR law, taking care that the process is not Poissonian. And maybe deciding that you have a 10% in 50 years is not physics. So all these messy messages to tell you that the future of seismic hazard can contain many more things. That's okay. I'm going to conclude with two slides, really. This is one showing to you how modeling can help us to improve. In 2 minutes I will finish. Can improve the source and set effect estimation. This is a modeling done pretty much long time ago now, because Kim Beck-Olsen did it in 2000. But he was using a 3D model of Los Angeles basin using different sources. So it's the same basin. In principle, set effect in one place should be one and just one. But considering 9 different sources, you see the faults here, okay? Where are them? Well, that's Northridge, 1994, an example. And this, you see the other ones, you see that the colors left on the ground, the hotspots, are totally different. Because source and propagation and site together, they can be highlighted in places that are totally different, as you can guess, just using physics. The final, so don't separate artificially source and site, especially when you are so close to it. Mexico City is extreme. The source is so far that actually that's just side effect. But when you're dealing with an extended source in a 3D basin, it's very difficult to separate source, site, and propagation. It's a mess. Final word is about PGA. Just two examples showing to you how PGA can be tricky. Let's give a look to this. That's Northridge, one of the most important events occurred in California. That's the time history acceleration. This is an earthquake that occurred in 1971 near Ancona. Now give a look to the magnitudes. Well, okay, 4.7. But nothing compared to 6.7, right? Well, we have the same PGA. But if you give a look to the two signals, they are totally different. One is very high frequency. A building, most of the important buildings, can be shaken, but no, nothing is occurring there. It's pretty much it's like this. You do understand? Okay, it's shaking, but it's not like that. Okay? So that's Northridge with Ancona. This is another case, again, Mexico, 1995, and an earthquake with, okay, a little bit less, but look at the signal and look at the signal. This is pretty much monochromatic with a period between 2 and 3. Give a look to the time scales here. You do understand this is 10 seconds, so that's very long. So amplitude is not that much, but it is at both periods. So you're hitting just the resonance. So a message to say to you that PGA, it has been used as an expression of lateral force, but it has been also abused because you do know that the acceleration time history can be changing a lot with frequency content for source and side effects. That's why I want to conclude with this slide here that is letting us to make a trip to Japan, where we will start on Friday discussing tsunamis here. Just to show to you the record in Tsukidate during the Toku March 2011 earthquake, and this is a sort of a world record, where in a tiny village, well, town in this part, Sendai is here, Tsukidate, and well, you know that the Japanese network has seismometers and accelerometers everywhere. Okay, give a look to this. Wow, 3G. Total destruction here. 3G is a parameter. No engineer can design something for 3G. And actually, these are the response spectra recorded in Tsukidate. Now you do understand what is this period of an hypothetical building with that resonance, okay? And this was the seismic code in Japan. The seismic code in Japan was developed after the Kobe earthquake. But look, it's taking care about these periods, not about these ones. Well, what occurred in Tsukidate was pretty much nothing. Some damage, definitely. But you see the tiny details. Well, except just tiny. Why? Because this huge acceleration was at very high frequencies. So all the local resonances in a building can be important. For an MPP, it's very important because, of course, you have implants there. Okay? Yeah, maybe some pipelines, some valves, whatever. But for normal buildings, those frequencies are pretty much nothing. They are huge, but at frequencies that maybe we can hear. I'm joking, but 20 Hertz is something that is going towards acoustics. So what I want to say to you, we will start on Friday again from Japan, looking at tsunamis. But one of the most tricky issues maybe is to choose the good indicator for an hazard assessment. Until 2000, it was PGA. Now it has been overcome by spectral acceleration because you can read the periods where it is important. And the engineer can say, okay, I have a bridge, I have a dam, I have an ordinary building. Okay, let's take the hazard there with SA at a given period. Okay? Please do remember your homework. 5 minutes, just to read again the net field small paper that you have on your website. Think about the different steps of a traditional probabilistic procedure. The case there discussed for 2 events, but in general terms, please think about when, from another curve, going to the final curve and you decide some percent in some years, well, you decide the return period. Return period of what? Second question. Third, if from 10 you go to 2, how much is this? Because this is what is used recently in US, for example. Not because US is the best, but just if you're going, if you're going there, if you're reading another map and you look at return period of 2,475, now you have an answer, but you have to prove it. You understand that it is a 2% in 50 years. There is no physics there, just statistics and Poissonian distribution. Okay, so you should have everything there. We did this, and in the last lecture we are going to deal, maybe in a short time, about a different phenomenon that is about tsunami, and we will speak a little bit about tsunami hazard. But for some reasons, it's much simpler, but, okay. Good work. Oh, I don't remember, have I pushed it? Yes.